All right, so welcome back. In today's video lecture for complex analysis, we want to cover the notion of complex powers. So this is the idea of taking a complex number z and raising it to some power, let's call it n. So how would we do that? Well, we don't really know. These complex numbers are quite exotic. So we're going to have a little bit of things that we can look at in our toolbox just to try to figure out what this means. And of course, to do this, we're going to make sense of the very profound formula that we found in the last video, or the 2 videos ago. I can't remember if it was last video or 2 videos ago, but we determined that e to the I theta could be represented as the cosine of theta plus I sine of theta. So we're going to build upon this idea and see if we can make any sense of it. Okay, so here we go. Let's start with powers. So we can recall from our earlier definition that z is equal to r times e to the I theta. So r is our modulus, and then e to the I theta represents some phase factor that gives us sort of how we rotate through the origin on the complex plane. Now, if you've taken a pre-calculus class or maybe studied a little bit of advanced calculus, you'll recall de Moivre's theorem. Now, this theorem says that z to the n, or well, we can actually define z to the n by splitting up the exponential term before even looking at the trig function. So we can just say z to the n is equal to r to the n times e to the I n theta. Now, if we want to go ahead, we can put parentheses around the n theta and the e to the I n theta and treat that as our new theta. And because of that, we can just plug that into the arguments of the sine function and the cosine function, which makes our lives fairly easy. So we have that z to the n equals r to the n times cosine of n theta plus I sine of n theta. So this is pretty easy for us now. We can determine any sort of power of a complex number by using this formula. So this should make sense, and this should make us pretty happy. But there is a little bit more nuance in the other side of things when we start thinking about what complex roots look like, which is what we're going to do now for the next part of the video. So if we consider a complex root, we will consider n now being some 1 over m. So instead of having z to the n, we have z to the 1 over m. And we're going to find roots, and we're going to call these roots zeta. So zeta, this squiggly Greek letter, is what we are going to denote as being one of the roots of z. It's going to be the mth root of z. So if I have, for example, if I want to find the square root of z, then it's going to be z to the 1/2, and then zeta will be the second root. Okay, so if we want to split this up once again, we get that zeta is equal to r to the 1 over m times e to the I theta over m. Okay, now this should make sense in theory, but it's actually quite nuanced, and to do that, we're going to consider more of a concrete example. So when considering the roots of a number, we now need to consider more than just the 2 positive and negative roots that we could get. For example, if I have the 4th root, so if 1 over m, if m equals 4, so if I have the fourth roots of 1, where I'm solving zeta to the 4th equals 1, well, then there are 4 solutions that will work, right? If I raise 1 to the 4th power, well, that's going to be e to the I times 0 times 1 to the 4th, which is obviously equal to 1. And then I also have I to the 4th. If I raise I to the 4th power, then I'm also going to get 1. It's 1 to the 4th times e to the I 2 pi. And we can keep going, and we see that we keep revolving around the unit circle to get back to 1, based on what our original number is. So if we consider this a little bit more interestingly, we can consider this being on a unit circle. So I'm going to scrunch this up to the other side a little bit. But if we consider a unit circle, I'm going to try drawing the unit circle. So there's our unit circle. And what we want to consider now is what our roots of 4 are, or what our fourth roots of 1 are. Well, we have 1 that's going to be at 1, and on the complex plane, so we're going to denote that as being a complex plane, we have 1 at 1, okay? We also have 1 at I. We also have 1 at negative 1, and then we have 1 at negative I. And so whenever we raise to the 4th power, we are going to be rotating, sending these little dots all the way over to 1, rotating around the unit circle. I find that to be very satisfying. If you consider, like, if I wanted the 8th roots of unity, well, you'd actually determine that the 8th roots of unity also lie on the unit circle and form, or they don't lie on the unit circle, but they form regular polygons at different, or they lie on the unit circle. There'd be one there, there'd be one there, there'd be one there, there'd be one there, and these would be the 8 roots of unity. So they all form these regular polygons on the complex plane that all rotate back to 1 when you multiply to the correct power. So all of this is to say is that there's a very nice way of writing things. If I have 1 to the 1 over m, which we call one of the roots of unity, so the roots of unity, because it's the root of 1, you can call 1 unity. So I would have 1 to the 1 over m being equal to e to the I 2k pi over m. Okay, so, for example, if I want to find cosine of 2k pi over m plus I sine 2k pi over m is going to be the kth root, or it's going to be the kth example of the mth root of unity. So k is some number that's going to run between 1 and m. And then m is going to be the root of unity that we're looking for. So for example, if I pick m to be 5, then I'm going to have 5 roots of unity, and by setting k equal to 1, 2, 3, 4, and 5, I'm going to find each of those roots of unity, just by using this Euler's formula. So this is what the complex root system looks like. It's a bit interesting, I would have to say, but it should make sense, and it should be very eloquent that it's being on the unit circle as well. Anyways, in the next video, we are going to move on to some additional topics in the complex algebra, and then we will move on to further topics in Unit 2. So thank you for watching, and we will see you in the next video.